Alrighty, good morning everybody. Welcome back to Linear Algebra. Plan for today, we're going to continue our standard 2 discussion of vectors and matrices. I've got my usual office hours today at 11 and at 1, tomorrow morning at 10 and at 1. Maybe after game. I have posted standard 2 problems on Canvas. You should be able to see them now. Post them as an announcement. So I encourage you to take a look at those. Plan is to finish standard 2 off probably in Friday's class, is the goal, with the expectation of doing a standard 2 quiz on Monday. Speaking of quiz, I have goodies to pass out. So let's see how many names I remember. Eleanor, Paul Joshua, Gabriel. Oh, you have 7. Ashley. Vince. Riley. Henry. Catherine. Joel. Abby. Cameron. Liam. And Wynn. Working on the names. Plan to get everybody down in the next week. So if I forgot your name today, please don't take too much offense. Okay, so before we jump back into standard 2, a couple comments I want to make on standard 1. First of all, the quiz. So the in-class standard 1 quiz, I asked you all to solve a system of equations, which a lot of you all did correctly or mostly correctly by putting it in matrix form, doing a bunch of row operations to get to this point where you said, aha, 0 can't equal 28, therefore this system of equations has no solution. And then a lot of you all said that this is the reduced row echelon form of the original matrix. But that is not so. It's close, but while it is, I think, relatively straightforward from here to say that the system of equations has no solution, why is this matrix not yet in reduced row echelon form?
The final row doesn't have a leading one.
Yeah, the first 2 rows have leading ones, but the last row has a leading 28. And that is no bueno. So, so you have a couple more steps. So first thing you need to do is you need to multiply the last row by like 1/28 or whatever to make this a 1. And then you can subtract off 2 copies of the bottom row from the first. You can subtract off 4 copies of the bottom row from the second to make these 2 entries 0. And because remember, if your column has a leading 1 in it, everything else needs to be 0. And then this was the actual reduced row echelon form of the matrix. So a lot of you all got, like what I would say, like 80% of the way there into finding the reduced row echelon form, but still needed to go through a couple more steps to make sure this last row has a leading 1 and that the rest of the column is 0. So the moral of the story is just because you have your matrix in a form where it's easy/straightforward to tell that it has, say, no solution to your original system of equations, doesn't necessarily mean it's in reduced row echelon form quite yet. And questions or comments about that? So Dr. Gerstle, my quiz has like a J or an M or an N at the top. What does that mean? Let me tell you all about the Gerstle grading scheme. You all got one of 3 letters on your quiz. You either should have gotten an M, which stands for mastery, a J, which stands for journeyman. Or an N, which stands for novice. Which sounds a little silly. And I took this from somewhere else. It sounds a little silly to me too. But the moral of the story is if you got an M for mastery, then you, well, earned a mastery on that quiz. Congratulations. So typically I'll give you an M if you got everything correct, or you got most, or you basically did everything correct. Maybe you made like 1 or 2 small computational boo-boos. Which, especially for things like row reducing these matrices, can be easy to do along the way. If you got a J for journeyman, that means you got most of the way there, you made a lot of good progress, but there's still something fairly important that I felt you were missing. And so that means keep going, you're almost there at a mastery level. If you got an N for novice, that means there's still something pretty major that you're missing. And you still have a ways to go by my estimate for that, in order to get a mastery for that standard. How does this affect my grade? So if you got an M, you've earned a mastery on that standard. Congratulations. If you got a J or an N, then both of those are going to affect your grade in exactly the same way, which is not at all. So if you got a J or an N, you didn't get your mastery yet, but like I said at the beginning of the semester, as long as you've earned 2 masteries in, say, Standard 1 by the end of the semester, it doesn't matter how many attempts it takes to get those masteries along the way. So if you didn't get your mastery on this first quiz, please, I encourage you, don't feel bad about it. Take that as a challenge to get there. I think most of you were at least 80% of the way there. I think you all can get those 2 masteries that you need, and you'll have plenty of opportunities. Again, 1 retest a week, plus each midterm and the final will have a standard 1 question on it that you can attempt to get a mastery. So keep that in mind. Dr. Gerstle, I got an M- or like a J+ or something. What does that mean? M-, as far as your grade is concerned, is treated exactly the same way as an M. It means you got your mastery. J+ is like you're on the borderline, but you didn't quite get to where I want you to be for mastery level. So for instance, if you row reduce the matrix correctly to the point where this had 28 and these 2 were some other numbers I can't remember, then I probably gave you a J+, because it's like, you got most of the way there, you did things correctly, you just needed to go and do 2 or 3 more steps. Whereas if you row reduced and you did everything correctly, except maybe like at some point you made a slight miscalculation, you said 3 minus 2 is -1 by accident, but you did everything else correctly, then I probably gave you like an M- to say, and technically this is not correct, but it's close enough. I know you know what you're doing. So that's kind of what the grading scheme means, and these are kind of the letters that I'll be using throughout the semester. Any questions or comments about that? As always, if you don't feel happy with your performance, do better. And no, that doesn't just mean like I'm not disappointed in you. What that means is, if you feel like there's something you're not understanding still, talk to your classmates, come by my office hours and talk to me. I'm happy to talk about anything that you feel stuck on. Come by and do retests. Especially like if you got most of the way there and you just forgot to make this last row leading 1 and then 0 out the rest of the column. If that's all, then that's something that you could probably fix easily on a second go around on your retest. So please, by all means, retest. Get those masteries. I want you all to do well. It means less work for me. Yes?
This is, I can get a dumb question, but you can.
Ooh, I like it already.
You can retest on the same standard, like even if you've already taken a retest.
You bet.
As long as it's just different weeks, right?
Correct. Yeah, so let's say, anytime you take the version in class, you may have noticed like there was a 1A on the quiz. The version A is always the in-class quiz, but if you come like and do a retest outside of class, I'll give you a version B. If you come in and then retest standard 1 again, which a couple of students already have, you get 1C, and so on. So yeah, you can keep retesting the same standard as many times as you want, with the provision that you can only do 1 retest a week, mainly for my sanity. But also so you take these retests seriously, or not just coming and saying, Dr. Ursula, I want to take 50 copies of Standard 1. Surely I'll get one of them right. If you try that, I will throw a piece of chalk or a pen or something at you. Any other questions or comments about the quiz, my grading scheme, etc. before we go back into Standard 2? Oh, one more thing. If you look on Canvas, I did actually update everyone's Standard 1 totals at this point. So your Standard 1 total should say 0, 1, or 2. Standards 2 through 19 are still going to be all zeros because you haven't had the opportunity to test on those yet. I'll update Canvas about once a week, usually on the weekends, with everyone's mastery totals. If at any point your total disagrees with what it's on Canvas, like if you think, Dr. Ursula, I got 2 masteries, it might be that I just haven't updated Canvas yet, but if I update Canvas and your score still seems wrong, send me an email. I personally, for my gradebook, have like a more detailed, like, oh, you didn't get a mastery on 1A, but you did on 1B and 1C. For you all you really need to know is just how many total masteries you have. So I don't keep track on Canvas of like, did you do 1A, did you do 1B, did you do 1C? It'll just say, you've earned this many masteries in Standard 1. Because that's all that matters as far as your grading the course is concerned. But if you have any specific questions, I do keep a more detailed gradebook for myself. Just feel free to ask. How can you tell if a clock is hungry? You can tell a clock is hungry if it goes back 4 seconds. Okay, so last time we talked more about vectors in Rn. We talked about how do you visualize in 2 and 3 dimensions. We talked about how to do 2 of the basic algebraic operations, take sums of vectors and do scalar multiples, where, as a quick reminder, if you have 2 vectors, v and w in Rn, and you want to add them together, you just add each component together. If you want to do scalar multiplication, if you want to multiply a vector in Rn by a scalar, meaning a single number, you can do that by just multiplying each of the components of your vector by that scalar. And we said that we had a special name for if you have a collection of vectors and you do some combination of these 2 operations. Anybody remind me, what is that called? Taking a blank of your vectors. Linear combination. So, before I move on to talking about dot products and taking magnitudes of vectors, which is kind of our next thing, I'm going to talk a little bit about what does it geometrically mean to add vectors, multiply vectors by scalars. In other words, using our sort of arrow picture from last class, what does it correspond to in, vector addition and scalar multiplication in a geometric sense? Because a lot of what I want to do in this class is to introduce ideas from different perspectives. Last time we talked about the algebraic definition of vector addition and scalar multiplication, but it also makes sense, I think, to look at it from a geometric perspective of how are you combining these 2 arrows together, so to speak, to make a new arrow. So let's say, what does it mean geometrically to add vectors v equals -1, 2 to w equals 3, 3 in R2? So for instance, if we have a vector w that points from the origin to the point 3, 3, and we have another vector v that goes from the origin to -1, 2, if we were to add these 2 vectors to get v plus w geometrically, would be -1 plus 3 is 2, 2 plus 3 is 5. What do we have to do with our two arrows for v and w in order to find an arrow for v plus w? Aaron?
Well, you would place vector v on the end of vector w or vice versa.
Ah, yeah. And so in other words, in order to add v and w, what you could do is go tip to tail. You start at the end of vector v and then travel out by vector w. Or start at the end of vector w and then travel out vector v. And where it ends, if you travel out v and then w, or w and then v, you draw an arrow from the origin to that point. That's going to give you an arrow corresponding to v plus w. Or at least it should if I were to draw this a little bit more accurately. But theoretically, this arrow should correspond to 2, 5 if v and w are drawn accurately and as you say. So if you go v and then w, or w and then v, and here's a situation where you would treat v and w as vectors not starting at the origin, if you're kind of adding it to another vector, you could get a picture that looks like this. What type of quadrilateral is being formed here, by the way? Yeah, it's going to be a parallelogram. You have two pairs of parallel sides corresponding to v, and another pair of parallel sides corresponding to w. And kind of the diagonal of that parallelogram is corresponding to v plus w, so to speak. So that's what it means to add vectors together, is kind of going tip to tail, one vector to another, forming the diagonal of a parallelogram, so to speak. How about if we multiply? Did some scalar multiplication. So what if we multiply vector v equals -2, 1 by 3? So what would it look like, the arrow that would be formed, if we were to take a scalar multiple of v, specifically looking at 3 times the vector v? What's it? Yeah, Eleanor?
You lengthen the vector in the same direction, so it's 3 times the length that it was before.
Yeah, in essence, multiplying a vector by a scalar like 3 means you multiply the length of your vector by that amount. So another way to think about it is we could put 3 copies of v on top of each other like this, and then the arrow formed going from the origin to where the third arrow ends would correspond to the arrow for 3 times the vector v. And finally, what if we were to multiply a vector, say, w equals -2, 4 by -1/2? So if our vector w to start is looking something like that, what would you expect to have happen geometrically to our arrow if we were to multiply the vector by -1/2?
Be on the other side.
The other side? What do you mean?
I'm saying if we're multiplying by a negative number, then it's going to cross over into the opposite quadrant.
Ah, so in other words, we're sort of reversing the direction of the arrow. So instead of pointing away from the origin that way, we're going to be going, instead of going up left, it's going to be going down right instead. So I think that'll account for the negative. How about the half? Henry?
Well, that would just half the length of the vector.
Yeah, instead of multiplying the length of the vector by 3, you'd be multiplying the length by a half. So we'd have a vector that's half as long and pointing in the opposite direction. So we'd be getting, in fact, 1, -2 would point something like this instead. So, moral of the story is, we multiply by a half by squishing the length down by a factor of 2. And the negative comes into play by just rotating 180 degrees about the origin. Or reflecting across the origin, reversing its direction, however you want to refer to it. The point is, pretty much every algebraic thing we do in this class is going to have a geometric explanation somewhere. It might be hidden, it might be sneaky, but it's there. You know how to look for it. When appropriate, I'm going to try and develop those connections as time goes on. Any questions or comments about any of these? In that case, let's do a dot product, which is one you may not have seen before, which is a little bit less intuitive, and you maybe haven't seen before if you haven't taken, say, multivariable. Where our first two operations are linear combination operations, give you a way to add two vectors, and to multiply a vector by a scalar. But the dot product is going to give us a way to multiply one vector by another vector instead. And so if v is in w, so if v is the vector, let's say v1 through vn, and w is w1 through wn, we can define the dot product of v and w. Is going to be a sum where you take each component of v, you multiply by the corresponding component in w, and then you add them all together. So you would take v1 times w1, you would add that to v2 times w2, etc., etc., and eventually you'll get vn times wn for your last term. Or, if you're feeling frisky, you could write that as the sum from k equals 1 to n of vk times wk, using the sort of sigma notation, the summation notation that you likely saw if you take in Calc 2. But the point is, you're multiplying corresponding components from each of your two vectors and adding them all up. Question. If you're starting with two vectors in Rn, two vectors that have n dimensions, and you take the dot product of those two vectors, where does the output live? Meaning, what sort of thing are we getting as an answer to when we take the dot product? A vector in Rn, vector in Rn minus 1. Abby?
Is it just a point in, would it just be R?
Something just in R?
Or would it be a point in wherever we are? I'm not sure.
Well, think of it this way. If we just look at v1 by itself and w1, what are v1 and w1?
Vectors. Oh, V1 and W1, they're just points.
Yeah, they're just
Yeah.
scalars, in other words.
Yeah, scalars.
Yeah, it's single values. If you take a bunch of scalars and you multiply them together, and then you add those together,
It's just a new scalar.
yeah, it's just a new scalar. So this expression, or however you want to refer to it, is a way of taking two vectors in Rn, multiplying them together, so to speak, and the result is a scalar. When you multiply two vectors together using a dot product, the result is not another vector in Rn like the original vectors. It's actually going to give you a scalar value, where the scalar value tells you something about the relationship between your two vectors. that eraser, more erasers. So for instance, ready? Chalk's getting steep. So for instance, if we wanted to compute the dot product of 1, 2, 3 and -4, 5, -6. If we wanted to use our dot product formula to multiply these two vectors together in order to give us a scalar, what would we have to do?
You would just add all the individual ones. So like 1 times -4 plus 5 times 2 plus -6 times 3. And then
Yeah, you just multiply the first components of your vectors together, multiply the second components, multiply the third components, and add them all up. So we get 1 times -4 plus 2 times 5 plus 3 times -6 is going to be -4 plus 10 minus 18, which is going to be 6 minus 18, I believe, is -12. It's going to be a scalar value -12, corresponding to taking the dot product.
Isn't like when you take the dot product, one of them is supposed to be the other way? Like one of the vectors is supposed to be like written from top to bottom.
It doesn't matter. If you're consistent about it when you take the dot product, whether you write it like this or if you were to write it like that. Now, if you're thinking about treating the dot product as multiplying two matrices together, then the order in which you do it does matter. And so, actually, in this case, I wouldn't like this. If you were to try and do like a product of two matrices, which we're going to be getting into in the second and towards the end of this standard, then it would have to be like one is written horizontally, one is written vertically. But if you just want to think about them as being individual vectors that you're taking dot products of, then it's okay to just write them out in that form. Good question, and that's one we're going to talk more about at the end of the standard, so probably in Friday's class. But for now, doing this sort of thing is okay. So, what would happen if we tried to take the dot product of 1, 2 and 3, -11, 2?
I don't think you can.
Not with that attitude. Well, we'd be taking 1 times 3 plus 2 times -11 plus times 2. You saying we can't do that?
Is the z value the first one just 0?
So sort of like what we said last time about adding vectors that have different dimensions to each other. If you really, really, really wanted to force the issue, you could say, oh, I'm just going to treat 1, 2 as being a vector in R3 by tacking on a 0 to its z coordinate or its x coordinate or whatever. And then you would be able to take the dot product. But as is, I would say you cannot take the dot product of these two vectors. Because in order to take a dot product, you need to have two vectors living in the same Rn. So this is, our first vector is a vector in R2. Our second vector is a vector in R3. So we can't do this unless we want to do some sort of shenanigans where we sort of sneak in an extra 0 at, say, the end of our first vector. But that's how do I put this? That is illegal to do until it's not. Meaning if you really need to take a dot product for some reason, you sort of can, but in general, it's going to break this formula because there's nothing in the first, there's no component of the first vector, for instance, as is, that you can multiply this 2 by right here. So I would say, for now, it can't be done. There may be cases that you'll discover later on where you would be forced to do so. So Dr. Gerstle, what does the dot product tell us geometrically about a vector? Turns out there's a lot that the dot product's going to talk about geometrically, and some of it we're not going to get into. Like, for instance, you can use dot product of v and w to tell you what's the angle between v and w. And in general, if you take the dot product and you get a negative answer, that generally means your vectors are pointing more in opposite directions than they are in the same direction. If you take a dot product and get something positive, that usually means your vectors are more pointing in the same direction than they are pointing in opposite directions. Does anybody know what it means if you take a dot product of 2 vectors and you get 0?
The same vector.
Not necessarily. If we were to take a dot product of a vector with itself, we would actually generally get something non-zero. In fact, we'd always get something non-zero unless we're working with a 0 vector. So the dot product of 2 vectors being 0 doesn't mean they're the same vector.
They're perpendicular.
Yeah, it's going to mean they're perpendicular to each other. Or, as a fancier way of saying perpendicular in this class, we're often going to use the word orthogonal. So for instance, if I wanted to take 1, 0 and take the dot product with 0, 1, 2 vectors in R2, that would definitely form a right angle. Well, that's going to come out to be a dot product of 0. And in general, that's the easiest way to check if 2 vectors are perpendicular to each other or orthogonal to each other, is just take their dot product, see if you get 0. If you do, neato burrito, you got yourself a right angle. If not, then sadness, you do not have a right angle. I mention this now not because it's super important for this standard, but because this idea of checking for orthogonality, checking for perpendicularness. Perpendicularness sounds like a silly word. That's why we say orthogonality. Checking for this sort of right angle condition is going to be super important for us in a few different contexts later in this semester. So I thought I'd mention it now. Questions or comments about the dot products? So, last thing I want to ask about is how to find the length of a vector in Rn. Because it turns out that if you take an arrow, you draw it out, natural question you might want to ask about it is how long is that arrow? So, for instance, I'm going to be on the next page of the packet. Say we wanted to look at the vector 3, 4. And this is our vector v. And I wanted you to tell me the length of that arrow. What would you do? Which Greek mathematician, in other words, would you want to invoke that would make finding the length of this arrow from tip to tail a little bit easier? Pythagoras. Yeah, Pythagorean Theorem. As it turns out, we do a little, we can form a right triangle here, where we know the length of this side is going to be 3. We know the length of this side is going to be 4. And so we could say that the length or magnitude of v is going to be what?
5.
How'd you get that?
The square root of 4 squared plus 3 squared.
Yeah, we know in this case that that 3 squared plus 4 squared should be the magnitude of v, quantity squared. So this by the way, I'll formally introduce a second as being the length of the vector. But if we want to solve for the length of v, we're going to get the length of v has to be equal to square root of 3 squared plus 4 squared. Or, 3 squared plus 4 squared. Dare I say, 3 comma 4 dotted with 3 comma 4. Because in general, if you dot a vector with itself, you're just going to square each component and sum it together like that. Which is, dare I say, square root of v dot v. And this is going to give us our more general formula for how do you compute the length of a vector in Rn in any number of dimensions. The way you would do it is sort of using this using a more generalized version of the Pythagorean theorem. You just take a vector dotted with itself, and then you take a square root of that. And that'll give you a scalar corresponding to the length of that vector. So if we write that down, we can say that for a vector v in Rn, the length or magnitude, and length and magnitude mean the same thing. Magnitude is maybe if you want to sound a little bit fancier, or if you're talking about earthquakes. But if you hear me talk about the length of a vector or the magnitude of a vector, it means the exact same thing. And the length or magnitude of vector v is defined to be v with sort of these double vertical bars around it. It's sort of like taking the absolute value, and that this should always return a non-negative scalar value. It's going to be square root of v dotted with itself. And this comes as just using a more generalized version of the Pythagorean theorem. In R2, this is exactly the Pythagorean theorem you're probably used to. But in R3 and higher, you can think about this as being a more higher order version of said theorem, where a squared plus b squared equals c squared if a, b, and c are the sides of a right triangle like this. So, for instance, if w is the vector 3 negative, why did I say 3 negative 4? It's like the exact same expression. Let's change up the numbers. Let's say vector w is 3 comma 100. And you want to take the magnitude of that vector. You can do that by just saying take the square root of 3 comma 100 and dotting it with itself, which is going to be the square root of 3 squared plus 100 squared, which is the square root of 10,000. 100 times 100 is 100 times 10 is 1,000 times 10 is 10,000 plus 9. Square root of 10,009. Which is very close to being 100, but ever so slightly more than 100 is going to be the length of that vector if I were to draw out the corresponding arrow on the board. A scalar value corresponding to how long that arrow would be. And the cool thing about this formula, square root of v dot v, is it doesn't matter how many dimensions you're working in. You can always just do that. So for instance, if vector v is 5, negative 2, negative 3, you want to take the magnitude, you take square root of 5 squared plus negative 2 squared plus negative 3 squared, which is the square root of 25 plus 4 plus 9, 29 plus 9, square root of 38. fun, I gave you the vector s equals -2. Vector in R1. What would the magnitude of s be in this case? All right.
2.
You take the square root of -2 squared, which is square root of 4, which is +2. In general, if we were to take the magnitude of a vector in R1, what are we actually taking? The absolute value. Yeah. So in R1, length slash magnitude means the exact same thing as absolute value. And so this notion of taking the magnitude of a vector, you can also think of as being a way to generalize absolute value to higher dimensions. So if I were to ask you to take the absolute value of this 5-dimensional vector, that's really what we're talking about doing. It's spitting out a scalar corresponding to somehow what is the length of that. Now trying to picture a 5-dimensional arrow might make your head hurt. But this is how you would do it algebraically. Any questions or comments? Groovy. So last thing I want to talk about, or actually I think that is the last thing for vectors. So that's kind of the first half of this standard. And these are going to be the algebraic / geometric operations that we do with vectors all semester. We're going to add them together, we're going to do scalar multiples, we'll take dot products, we'll do find their magnitude. But Dr. Gerstle and multivariable, I learned about the cross product. When are we going to do that? We're not really going to talk about cross products much in this class. So I'm going to skip that so I don't have to spend a whole class introducing the cross product and then barely ever using it. But if you've taken multivariable, you've likely seen another operation called cross products, which is a way of multiplying vectors together to produce another vector. And it tells you a lot of cool, fun geometric information, but that ends up usually being a little bit more relevant in multivariable calculus than it does here. So we're not going to talk about it unless we need to. Because it's a little bit more complicated than these operations we talked about, both algebraically and geometrically. So with that in mind, I'm going to talk about matrices some more. So we've already seen matrices in the context of standard 1 as being these rectangular arrays of numbers which you can manipulate in a certain way to help you solve systems of linear equations. Going on through linear algebra, the entire semester is not going to be focused around how can we use matrices to solve systems of equations. We started off that way because that's kind of where the initial intuition of a matrix comes from, is its use in solving this sort of system of equations. But since then, matrices have come to mean so much more. And we're going to be exploring a lot of the so much more throughout the semester. So, just like how rest of standard 2 is how to algebraically manipulate matrices. So it may be a shock that just like how you can add two vectors of the same dimension and multiply a vector by a scalar, same is true of matrices. You can add matrices, you can do scalar multiplication of a matrix, and it works basically the same way. I don't really feel like writing down this definition, but so let's just do an example for scalar multiplication. If I were to give you the matrix 4, 6, -3, 0, 1, 9, and multiply by -1/3 as an example of scalar multiplication for matrices, what would you expect to have happen? In other words, what would your intuition tell you how would you multiply a matrix like this by a scalar like -1/3? Okay?
Would each of the individual values be multiplied by 1/3?
Yeah, exactly. It's basically the same as vector scalar multiplication. You just take all the components of your vector and multiply by that scalar. Same's true for a matrix. You take your matrix, you multiply each element in every row and column by that scalar. So in this case, we get back another 3 by 2 matrix. -4/3, -2, 1, 0, -1/3, -3. You just multiply each entry by your scalar out front. Just like you would with vectors. Matrix addition works basically the same way. If I were to give you, let's say the matrix 1, 4, 7, 3, adding that to the matrix 0, -6, 5, pi. I went to pi to spice it up a little bit. What would you expect to be the top row of the sum matrix?
1, -2.
1, -2. You add component-wise. And let's see, Gabriel, how about the bottom row?
12, 3 plus pi.
What is 3 plus pi?
6 point something.
6.1415. You can tell a mathematician from someone who just likes thinking about math. Someone who likes thinking about math will have like 100 digits of pi memorized. A mathematician will be like, pi, that's like 3-ish or something, I don't know. But the moral of the story is, if you want to add two matrices together like this, just like with vector addition, you just add the corresponding components together there. Same's true here. You add the top left entries, top right entries, etc., and that'll give you matrix addition. Questions, comments, concerns? What do you think it means to do a combination of these two operations to a collection of matrices? What did it mean to do the combination of these operations to a collection of vectors? Linear combination, yeah. So any combination of these two things we call a linear combination. And I mean, it's basically the exact same as it is for vectors. You just have these sort of higher dimensional things where you have sort of rows and columns instead of a vector, which you would just treat as being like a single row or a single column. But the intuition is the same for how linear combinations operate. You take sums of matrices and you potentially multiply those matrices by scalar values in the same way. Where scalar multiplication, once again, just means multiply each component by that scalar. Addition just means add all the corresponding components to get a thing of the same size that you started with. So there's two more operations for matrices we're going to be looking at least for this standard. There's something called taking the transpose of a matrix, which isn't too bad. And then taking products of two matrices, which is a lot more exciting because it's not nearly as simple as just multiplying the corresponding components together. Multiplying matrices is in fact going to get us into a lot of mischief for the rest of the semester. And on Friday we'll talk about how you do that. So on Friday we'll talk about matrix transposes and matrix multiplication, and that'll finish off standard 2. In the next standard, we're going to talk about, just give you a sneak peek for next week, linear transformations. How you can encode different types of functions using matrices. How you can encrypt and decrypt secret messages using matrices. You all have a good one. I'll see you all on Friday.